to recap what we had yesterday was essentially this formula right here. Okay? Find the volume of a solid by slicing. So the idea is we're using the integral to add up these slices. So if we took like these two things right here, right, just solid plastic, we want to know how much plastic is in these. Now, for example, an engineer, okay, you're an engineer and you're designing a part for some machine, and you've got to do a cost analysis as part of your report on this thing of what this is going to cost. And so you've got this material, whatever your material is, and how much that costs. You need to know the volume. You need to know how much plastic is going to, metal or whatever it is going to be involved in this. So you've got to know this volume. Now, if it's something like this, yeah, you can dunk it in water and you can do a displacement. But if you're designing something that doesn't exist yet on a computer, you can't hardly dunk it in water, right? It's on a computer. Or if you have to get on the screen, dunk the computer. If you've got if the part is, or the thing you're designing is as big as this room, you're not really going to do water displacement to find its volume, right? So especially in that computer example, you've got to have a way to mathematically represent this thing. I mean, you can even see this particular thing. Almost looks like you'd have kind of a sine. It almost looks like kind of a sine curve, kind of a shape for this one part here. I mean, obviously this part's easy, the cylinder part, but you've got this here. Here you might have, this could be, part of a sine. This could be a parabolic shape here, that kind of thing. So how are we going to find this volume? Well, mathematically, if we could represent, like I say, these curves, which you would do as you're designing this, then we could use this idea here to create these volumes. So as we look at these two pieces here, if we were to slice these this way, they would have circular slices, right? Of course, in the cylinder, they'd all be the same, and then in here, they'd be different sizes. Same thing here. So just like we did with the lemon yesterday, we sliced it up, we added up the volume of those slices, we used the integral to add up those slices, all right? So what we came up with is the integral is going to add up these slices. Well, each slice is going to have its cross-sectional area times its thickness. So if they're circular slices, it's pi r squared h. But what's the h? We found out yesterday. What was the h on those slices, the thickness? That turns into the dx, right? Because when you slice that thing to an infinite number of slices, the slices get paper thin, almost down to no thickness whatsoever when you have an infinite number of them. So the dx becomes the thickness. So it's the area of the slice, and the dx represents the thickness. Those two multiplied together gives you volume, and then the integral adds up all the slices, giving you the total volume of the solid. That's the idea. So what we need to be able to do then, the key to this is this right here. We need the area of the slice. So we need to know what the shape of the slice is. Okay? So this method only works when the slices all have the same shape. All right? So the most basic one that we've worked on so far then is, say we have this solid right here. So we have this blue region. We're going to revolve, and so these are called solids of revolution, like you see I wrote over here. Okay, so when we take a region and revolve it around an axis, that's going to create circular shaped slices because of the act of revolving is what makes the circle. So here you can see the slice. And of course you would have a lot of slices throughout there. So if we add up all those slices, we get the volume of the entire thing. Okay? So we need the area of one slice. Well, a slice is pi r squared in this particular problem. So what we did yesterday is we said, okay, if I'm going to do this, here's a slice, this circle right here. Let's use red. So this strip right here is the radius of that circle. Let's call it r of x. And that radius is the top y value, which in this case would be square root of x, minus the bottom y value, which is 0. So our integral was pi times the radius squared, this is our radius, and then dx is our thickness, and then those strips go from 2 all the way out here to 9. And so for this particular problem, this would be our integral that would give us the volume of that solid. Okay? So the key to it is the strip. What does a strip represent? In this case, it represents the radius of that slice, the radius of that circle. The area of a circle is pi r squared. So following that formula we had up a minute ago, the area of a slice is pi radius squared times thickness gives us volume. Okay? And then now, from there, just type into your calculator. Okay? Now, you'll look up, when you look in the answer book, you'll see they work them out. Because this is from an older book where we used to, you know, they're set up to work pretty nice. And the square root of x squared is just x. And so antiderivative would be pretty easy. So when you see them in the book, they're going to work them all out. Don't worry about that. We're going to type in the calculator. I just want to make sure you set them up. We're going to type in the calculator, get our answers out. All right, so go to your homework. So we're going to come back and put this in our notes here in a little bit. Okay, so on your homework now, on the homework, which was on page 419 in the LH packet, they already had the picture drawn. They already have the strip in there for you. That's normally not going to happen. Normally what's going to happen is you'll be given a region to draw. So it'll say something like, okay, take the region bounded by the line y equals negative x plus 1 and the x and y axis in the first quadrant. Something like that, they would say. And then they would say revolve that region around the x-axis, find the volume of that solid. So we would take a strip and put it in here like this, and imagine, if you will then, what this solid would look like. What would this solid look like? It would be a cone, because here would be the other half of the solid right here. And so what we would have, and it doesn't matter if you draw this or not, but basically what we would have would be this cone right here. And our slice, if we were to slice it, would look something like, that's not bad, a little slanted, but that would be a slice. Slice, 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 like so. This would be a slice, and it would be a circle. And this strip is what? The radius of that circle. So you don't have to draw what the three-dimensional piece would look like. You don't have to draw the other half of it, okay? But in these early stages, I'm going to do that because I want you always to be visual. I don't really want you to just memorize, oh, you just do top minus bottom and plug it into this formula. I want you to imagine what's going on, okay? There are slices of this solid of which this strip is the radius of the circular slice. So what we need to follow our formula, which is the area of the slice, right? That's what we need. Well, the area is the area of a circle. So I like to just, I'm going to put R here. The top y value is that right there. So it's negative x plus 1. The bottom y value is 0. Top minus bottom. I always like to do that just to remind myself I'm doing top minus bottom. Okay? So there's my radius. So it's going to be pi. It's going to be radius squared times thickness. And those strips go from where to where? 0 to, what's that? What was that point right there? 1. And there you go. Now you can put the pi out in front if you want. Okay? I like to leave it inside so I remind myself I'm doing pi radius squared like so. Okay? Number 2. Revolving around the x-axis again. So again, here would be the other half of my solid. It would look something like that. Basically, this would be a slice right here. And so that strip, again, is the radius. So it's simply my radius. I like writing it out here. I know in these easy ones it seems kind of ridiculous, but I'm doing top minus bottom. You're going to see as we get into some more complicated ones today why that's an advantage. I'm going to write out my radius. It's my top minus my bottom. So when I come to put it over here, I've got pi, and then I've got radius squared, and they go from 0 to, what is that, 2? So the strips fill the space from 0 to 2. Now we should check these, make sure we're getting the right thing going on here. So number 1 was pi thirds. Number 2 is 256 pi over 15. Okay. Then we go on to number 4. Number 4 said, okay, and again, normally it would be, okay, take the region between the x-axis, or bounded by the x-axis, y equals x squared, and the line x equals, what is this line? X equals, what is it in your packet? X equals what? 1. X equals 1. Okay? So we're going to revolve that around the x-axis. So again, the other half of our thing, this would be kind of a weird looking, kind of a cone, kind of a thing. That would be something like that, like a trumpet maybe or something, sort of thing. Okay, and your slice would look, the slices would be something like that right there. Where again, that strip is the radius of that slice. So top y value minus bottom y value would be my radius. So it's simply pi times radius squared dx, and that strip fills that space from 0 to 1. That's it. Okay? That's it. That's all there is to it. Okay, then we go to number 9. And let's see, what was that answer? What did you have for number 4? Pi over 5. Okay, number 9. Now we switch, and we're going to revolve around the y-axis. Okay, so now we're talking about this. This would be our solid. So now a slice would be in here like this. So what does that mean? What's changed? The rate, yeah, but I mean, horizontal strips, right? We've got to use horizontal strips. In other words, our radius is going to be right here. Well, that's a horizontal strip. So that's just like we were doing last week. That's a right minus left. So I need this x coordinate. Well, what is this x coordinate of the parabola? How do I get the x coordinate? I have to solve this for x. So I square root. It'd be plus or minus, but this would be the negative side over here. This would be the positive side over here. So it'd be x equals square root of y. So I need to take the right x, so my radius is my right x coordinate, which would be root y, minus my left x coordinate, which is 0. So there's my radius. So now I got pi times radius squared, oops, that'd be dy. And the strips go from 0 to 4. 0 to 4. So when we get horizontal slices, when the slices are this way, horizontal, that means I have horizontal strips. So I have to do right minus left instead of top minus bottom. But all that work we did on right minus left and top minus bottom last week comes in really handy here when we do these areas. Okay? All right. Last one then, we have a quarter of a circle. We're going to revolve it around the y-axis, which this is a nice one to check, because now when we revolve this, we're going to get we're going to get a semicircle, right? Now or a semisphere, right? Half of a sphere. Does anybody remember what the volume of a sphere is? 4/3 pi r cubed is a sphere, but we only have half of a sphere. So it'd be 2/3 pi r cubed, right? And this one has a radius of, looks like 4. So this would be 2/3 pi times 4 cubed. Well, 4 cubed is 64. So this would be 128 pi over 3 is what we should be getting on this problem. Okay? But let's set it up as an integral. So here is our equation right here. We're revolving around the y-axis, so our slices have to go this way. Here would be one slice. It would be a circular slice. This strip, I don't care if you draw these circles and stuff I'm drawing in here, really the strip is all you really need, but I want you to see that when we do this strip, we're really doing the radius of this circle, radius of this slice. So my radius is the right x coordinate. Well, we need to solve this for x, so we better square both sides. We better subtract the 16. It'd be smarter to add the x squared over to here and subtract the y squared. And then square root Oh, we get basically the same thing, okay? Makes sense because of that symmetry. So my right x-coordinate is square root of 16 minus y squared minus my left x-coordinate, which is 0. So the integral is pi times the radius squared dy, and the strips fill the space from 0 all the way up to 4. Okay? Like so. And type that in your calculator, you better get 128 pi over 3. Oh, and by the way, what was number 9? 8 pi. 8 pi. All right. So here's the next one I want to do. So in your notes, go ahead and get your notes out probably. We're going to do some examples. Now, I want to do this one right here. Let me reset this. I'm going to do one here that we can see a picture of. All right. So here would be the directions for this problem. Okay, the directions for this problem would be well, it would say something like this. The following region is bounded by y equals square root of x, y equals 0, and x equals 4. Okay, those three things right here. Okay, so you would have to draw, and you would have your calculators if you needed to. So you need to draw y equals square root of x equals 4, and of course y equals 0 is the x-axis. So that tells me that this is the region that I am revolving. Okay? And then it would say, find the volume of the solid when that region is revolved about the line y equals -2. So we're going to revolve it around that line there. Now, you guys, we talked about this. Some of you, I mean, Doug, you asked about it, I think, yesterday. What changes things here? Or what is changed here? Where the axis of revolution is, which causes what kind of a change in our picture, in our solid? It's hollow in the middle. There's empty space. So our slices look like what? They look like rings, donuts, washers. A lot of times the term is washer. Okay, you notice here they say sweep one disc / washer. Okay, so these are typical discs and washers. We can call them circles and rings or whatever. But when we revolve this region, we do in the sense then that, yep, there is some empty space in there. And look at our slice. Look at our slice right there. Okay? Our slice is just a ring. Okay? So let's quit revolving that. Let's just look at, I don't want to do that. All right. So but again, nothing has changed here as far as what my formula is. My formula is still the integral of the area times the thickness. The thickness is dx. All I need is the area of a ring. Well, how do you do the area of a ring? When I talk about the area of the ring, I'm talking about this area. I'm talking about the area of the solid, right? When we find these volumes, we're finding the volume of the solid, not the space inside. You know, like when you find the volume in a bottle, you know, like a bottle of water, the volume is the empty space inside. How much liquid can it hold? That's not what we're finding. We're finding the volume of the solid. Okay? So we don't want this inside stuff. Whoa. Killed myself. Could have been bad. All right. How do I find this red area? The big circle minus the little circle or the inner circle. So here's how I'm going to write that. So the area equation is now changing. Let's write it this way. Okay, big R for the outer radius and little r for the inner radius. Okay, so our integrals are going to change depending on our slices, right? All the problems we had today had solid circular slices. There was no empty space in there. If there's empty space, then your slices are going to be washers. There's going to be empty space. And so this is what's going to go inside the integral now. So we need big R and little r. Now here's what's interesting about this is the strip in this problem, the strip is right, I don't know what color would work best. There we go. That's the strip, right? Here was our region. Here's our strip right here. Is that the outer radius? Is that the inner radius? Is that strip either one of the things we need for our formula? It isn't. We need new strips. We need different strips. That strip doesn't even apply here. Where does a radius always have to come from? The center. Where's our center? Down here. So what we're going to have is two strips. That one is going to be our outer radius, and this one is going to be our inner radius, right? A radius always has to come from the center, okay? And the center is the axis of revolution. So we have to draw new strips. Now, it's easy for me to see that on here. But you guys aren't going to have that capability. You're going to be dealing with a problem like this, right? This is what it's going to look on your paper. Now, if you want to draw the other half of this is going to be down here, right? Going to look something, oh, that's awful. But the other half, and so what's one slice going to be? One slice is going to be like this, right? That's going to be a slice. Here's your center, okay? And now, I should draw the other part of the slice. That's not bad. That's not bad. Okay? There's going to be one slice right there. This ring. Okay? That's going to be a slice. So we need the outer radius. So the outer radius is going to go up to here, and the inner radius is going to go to there. So you need to draw both of those. Okay? So there's still strips. There's still strips. It's still going to be top minus bottom and right minus left. But it's just not going to be the strip we're used to. We're used to doing our strip inside the region. Well, that only applies here if the axis of revolution is here. And sometimes I like to do this. Think about like a pin. So if this is my axis of revolution, and here's my strip, and it revolves, see, that's going to create a solid circle. And so the strip is the radius, right? The strip is the radius. But now, if my strip is up here, if this is my region up here and I revolve it, see, I've got that empty space. Well, now the strip, the marker here is not a radius at all. The radius goes from here up to here, the outer radius, and the inner radius is a smaller piece, okay? So that's what we got going on when we revolve these. So anytime we revolve a region, it's got to be one of those two things. There's either empty space or no empty space. If there's empty space, it's going to be a ring. If it's no empty space, then it's going to be a solid circle, okay? All right, so let's finish this one out, and let's write it down. So what's big R? Big R would be this strip here. So what is that? Root x minus -2. So plus 2, right? It's going to be top y value minus bottom y value. So it's root x minus -2. So that's going to be root x plus 2. What's little r? 0 minus -2, which of course is just 2. And that is, you can see that all the way through here, the inner radius is going to stay the same, right? That's not always true. Sometimes the inner radius changes too, all right? But here it doesn't. So now we set up our integral. Here's when it's not a bad idea to put the pi outside. Because what I need here is I need my area equation is pi. Here's how I'd want to do it. It's pi big R squared minus pi little r squared. Now, is there any reason to write pi twice? I think we can pull the pi out and write that as big R squared minus little r squared. I think that's probably a smarter way to write that. Okay? And then, when I put it into my integral, I can just pull the pi out in front, and now I can do big R squared, so root x plus 2 squared minus, and then little r squared, right? It'll look like that. So what I'm doing is my pi big R squared minus pi little r squared. Let's pull the pi out. You got big R squared minus little r squared. And then I can pull my pi out in front of the integral, so I got big R squared minus little r squared. This is where it really comes in handy, I think, to write your big R and your little r separately, top minus bottom, look at the strips. And then that goes from where to where? Zero to 4. Okay, because those slices are going to fill, okay, from 0 to 4. And then type that in your calculator and see what you got. I'm not that concerned about that. That's easy to do right at that point. It's setting it up properly is what we care about. Now, when we get to our quiz on this kind of stuff, probably like a 4-point problem. You're going to get a point for getting this integrand right in here. You're going to get a point, well, probably, yeah, maybe 2 points for the integrand. You know, you got to remember the pi. You got to remember this squared, that squared. So if you have one mistake somewhere, it's -1. You have another mistake, it's -2. So probably 2 points for that in there. A point for the 0 to 4, getting that properly written, and then your final answer. Okay. Sometimes even a sketch. Okay, that might be worth something on the problem too. So it could be 4 or 5 points there. Okay. All right. So that is a washer or a ring problem. Let's go back to your notes here. And let's start a list of the types of slices that we could have. So right now we've got 2. Okay, we've got a disc or a circle, a solid circle type slice. Okay, so that could look like, you know, that's where you have a slice that goes like so, and it's solid all the way through. And of course the area of that is pi r squared. Okay, and your r, of course, goes from the center, you know, like so. And then the other thing is we could have a washer type slice, or a ring, if you want to call it a ring. And there, you know, you're looking at something like that. And again, you've got an outer radius and you've got an inner radius. So that's pi parentheses big R squared minus little r squared. So those are 2, and you're going to basically have to memorize these for our next quiz. You know, and we're going to add. We can have solids that have square slices or triangle slices. Now the difference is those would not be solids of revolution. Those would not be formed by revolving in region. Okay, those would be formed in a different way, and we'll get into those probably next week. We'll see, because I want to get into some. I'll probably show you some of those today, actually. But I want to go through and work a couple from your from some of your packets. Well, I take it back. Let me just show you some right now. Let me show you some right now. Might as well just look at a few. Okay, but then I want to practice some. Because the disc and the washer ones happen most often, so I want to spend most of our time working on those. But let me show you what it would look like to have something that had a different kind of a. Okay, these kind of problems would be worded differently now. So it wouldn't say revolving. The word revolving would not be in there if we're going to have a different sort of thing. It would be something like this. It would be it would describe the region. They would say, okay, here's the region formed by, in this case, the region inside of this square, or excuse me, this circle. The region inside of this circle is the base of a solid. That's what it would say. This is the base of a solid. And the solid has, and what do they say here? The solid has square cross sections, which means square slices. Now, what that is saying then is that coming up off of the board here would be squares to form this solid. So if we sliced it like, let's see, what did it say? Perpendicular, I think perpendicular to here. So it'd be like this. So if I slice this way, okay, there would be squares coming up off of the board. Now it's hard to envision that, so this is kind of cool how this little thing works here. So, okay, these would be like your strips. Here would be a strip from here down to here. Now remember, we got two halves. We got the top half of the circle, which would be positive square root, and then we got the bottom half of the circle. So there's two curves here, basically. Okay? Again, this is the base of the solid, and rising up off of that base are squares. Okay? This allows us to see it three-dimensionally a little bit. Now try to envision that. You've got squares rising up off of this. Okay? Let me put a couple of them in there. Does it make sense? You have smaller ones down here, right? Because they're squares. So the strips that we had drawn are essentially what? What part of the slice is the strip? It's one side of a square, right? The strip, remember in the problems we've been doing, the strip is the radius, right? Or in a ring, the strip is the outer or the inner radius. Here, the strip is going to be one side of the square. Okay? Let's see if you can rotate it a little bit so you can kind of see that. Okay? Here would be one square sweeping through the whole thing. Now what would this, what are you picturing here for this? What would you call it? What would it look like? Thingamajig? Right? Now, because this is here because of the corners of the square, right? The corners of the square is in here, but it's round. It's still rounded. It's curved all the way around because its base is a circle, right? If you put those four squares back in there, right? So again, we're slicing it like this, and every slice is a square. So there's no revolving going on. There's a region that is the base, and rising up off of the base are these shapes here. Okay? Well, the formula is going to be the same. The formula is going to be, it's not going to be pi r squared. That's for a circle. The formula is the area of a slice times the thickness. Well, our slices are squares. So what's the area of a square? Side squared, right? And what is a side? Isn't the strip the side? So isn't one of these the S? So the S actually literally could stand for strip, right? So the strip, so instead of calling it R in this problem, we would say, okay, that'd be square root of, and they just call the radius r, so we'll just r squared minus x squared. We would actually have numbers there. Minus, and then the bottom is the negative square root. Well, that would end up being plus, so the strip would actually be 2 square root That would be the strip. But the strip's not a radius this time. The strip is one side of the square. So in our integral, we would simply take that squared, pi, right? It's not a circle, right? It's just that squared, and the strips go from, in this case, negative r to r. We would probably have numbers in there, like -2 to 2 or something like that. You see what I mean? So now I don't know that we're going to have, we might do a problem where we got a couple of these today. But so you can have square strips. So let's go back to our notes. Let's go back to our notes and let's add that as a third one. We could have square slices. Okay, and so that's a little harder to draw. Give it a go. Okay, and the area of that is s squared. So we would have a region, and coming up off of that would be squares. But again, the key is the strip. What does the strip represent? So far we've had three things. The strip can be in there and represent the radius. In a ring, you have two strips. One is the outer radius, one is the inner radius. In a square, you have one strip, and it's the side of the square. Okay? And so you find the strip and then apply it to the appropriate formula. Let's look at another one here. Let's do same base, except this time the slices are going to be equilateral triangles. So there's your strips. Let's lay it down so we can see it. Coming up off of there are equilateral triangles. Like that. Okay, but again, you can see coming up off of the circle. So when you guys, obviously, when we draw them on our homework, you're not going to be able to, you won't, you could try to, but basically you're going to have the region. You just have to envision this coming up off of the page. Well, now what's our strip in this? What's a strip? Oops. The strip is the side of an equilateral triangle, right? It's the side of an equilateral triangle. Now, the question is, what in the world is, so we would do the same thing we did earlier. We would do our strip, which remember was 2 square root of r squared minus x squared, right? It was top minus bottom. But this time that strip is the side of an equilateral triangle that's coming up off of the thing here. Okay? Well, what's the formula for area of an equilateral triangle? Now, why are we doing that, not just a regular triangle? Well, because a regular triangle, then you got half base times height. Now you have two things you need, base and height. It's easier if we just stick with one thing, okay? And so that's why we go with equilateral triangle. Well, it looks like this. If this is your equilateral triangle here, if you divide that in half, you get a 30, you get a 60, right? This would be 1/2 s here. And if you remember your ratios, right, 30-60 triangle, this is 1, this is half, and what's this one? Across from the 60. Root 3 over 2. So this would be root 3 over 2s. So this triangle would have the area 1/2, the base would be s, and the height would be root 3 over 2s. So it's root 3 over 4s squared. And that's one we're just going to have to memorize. So we're only going to have a handful. So let's go back to your notes again. Fourth one in our list is going to be an equilateral triangle. So we could have slices that are equilateral triangles, and the formula for that is root 3 over 4 s squared. All right? Let me show you one more. Different region this time. And we're going to be perpendicular to the y-axis, so we're going to have horizontal strips. This time, this is the base. So it says this is the base of a solid whose cross sections perpendicular to the y-axis are semicircles. So now coming up off of the base are semicircles. Okay? Can you see what that'll be? Kind of? How would you describe it? Half a cone, except it's more of a right-angled cone. You know, a cone would go like this. You know, it would angle down from the tip this way. This is going to be a right angle on one side, right? Because there's a right angle here. This side is diagonal. So sort of that kind of thing. So it would look something like this. Okay. It would kind of have that cone kind of shape, but it'd be a right angle on one side. There's not really a quarter of a cone either, because these are still half circles here. But basically, here's your solid. Here's your semicircles in there. Here's your strip. Now, what is your strip in this? It's the diameter of the slice, right? So what is the area of a semicircle? Well, a semicircle is 1/2 the pi, oops, don't forget pi. That's a semicircle, right? That's the area of one of these slices. It's a half circle. So it's 1/2 pi r squared. The problem is our strip is the diameter, right? So we're going to have to do one of two things. Probably the easiest thing is to take your strip, and that's your diameter, and then divide that by 2. So then you have your radius. And then you plug it into here. So you got to be careful. You're going to have 2 1/2s in there. You're going to have a half here because you're going to take half your diameter. And then your formula has a half in it because it's a semicircle. So let's take a look at we won't get into a problem like that probably yet for today. But let's add it to our list here. So we could have semicircle slices okay, semicircle slices, and the formula for that is 1/2 pi r squared, but we got to keep in mind that our strip is going to be the diameter of the semicircle. So whatever our strip equation is, when we do our top minus bottom or right minus left, we're going to take half of that. That's our radius. Then we're going to plug it into that. Okay? So those are the 5 that you'll be responsible to know for our slices. So our overall formula is we do the integral. Inside the integral, we want the area of the slice. That comes from our strip, so it's going to be one of these 5 equations that's going to go in there, because those are the types of slices we're going to do. All right, get out your 2011 packet, and I think also your 2013 packet. I think those are the 2 I want to do today. And then we're going to have some work time. All right, problem number 3. Problem number 3 in 2011. We're going to do part C that we have not done yet. All right, let R be this region enclosed by these curves. Okay, so here's our region. we're going to revolve this region around the line y equals 1. Right? But do not evaluate an integral expression for the volume of the solid generated when r is rotated about the horizontal line y equals 1. So here's the horizontal line y equals 1. So what kind of a slice are we going to have? The vertical strips, what shape is it going to be? It's going to be a ring, because you got this empty space, right? Here's going to be the other half, if you want to look at it. The other half will be up here, something, like that, whatever. It's going to be this kind of a, thing like so. Your slice, one of your slices will go up here and down here, right, like so, and then here to here, right, is that empty space. There's going to be empty space in there. And so there's a slice. It's going to be a ring-shaped slice. It is not necessary that you draw all of this stuff. You just have to understand, you wouldn't need any of that up there. You just have to understand that we are going to have empty space. Anytime that the region is not setting right on the axis of revolution, okay, when it revolves, this empty space will be in there. That's going to create a washer. Okay, so we need 2 strips. Outer radius is going to go to there, and the inner radius is going to go to there. Right? The outer radius goes from the center to the far outer edge. The inner radius is basically the empty space, right? The inner radius is in the empty space. So what's big R? One. No. It's always minus, right? Top minus bottom. So it's 1 minus, which function is that? The f of x, the 8x cubed. So 1 minus 8x cubed is the outer radius. 1 minus 8x cubed. The inner radius, one minus sine of pi x. So my integral will be, remember our area for a ring is pi parentheses big R squared minus little r squared, right? That's our area of a ring. So pi on the outside, then it's going to be big R squared. There's big R right there, minus little r squared. And I think this is a no calculator one, so you can see why they would, that'd be a real mess to try to do. And that's why they say write it out, but don't evaluate. And then that goes from where to where? 0 to 1/2, right? The strips fill the space from 0 to the x coordinate there, 1/2. 0 to 1/2. Horizontal strips would go from 0 to 1. But we want vertical strips, 0 to 1/2. And let's take a look. Is that what they have here? Pi, 0 to 1/2. Sure enough, that's exactly what they got. Okay? All right. There you go. Very good. That's the 2011. Let's go to the 2013. Now again, most of your homework today is going to be these revolution. They're going to be disc or washer. I am going to give you one or a couple of them that are these other square ones, and we'll try to work on those. Okay? All right, 2013, let's go down. I think it's problem number, there it is, 5. Problem number 5. All right, let's do part B. Write but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals 4. Okay, there's the horizontal line, y equals 4 right there. We're going to revolve it around that. So which way are the strips? You don't have a choice, right? You're revolving around a horizontal axis of revolution. Which way are your strips? Vertical. They got to be, right? They got to revolve this way. The slices got to go perpendicular to that. Okay? So they've got to be perpendicular. The slices have to be perpendicular. Okay? So, disc or washer. There's empty space, right? There's empty space in here. Here's your region. That's the solid material. When we revolve that, right, be up here, this is all empty space in here. So, strips, your radius always comes from the center. Oops. Redo that. Okay, so my outer radius is going to be what? Let's just use F and G here instead of writing the whole thing out. Which one's the top one? G's the top one, isn't it? So this one is going to be 4, so the outer radius is the top y value, which is 4, minus the bottom y value, which is this curve, which is the F graph, right? G's on top, so that's the F graph. Okay, that's the parabola. So it's going to be 4 minus F, and little r is going to be, because you'd really have to make sure and use parentheses here. When you go to type in your calculator, you know, you'd have to go 4 minus this quantity, right? You have to make sure and do that, so it gets kind of messy. And what's little r? Well, it's top y value, which is 4, minus the bottom y value, which is this 4 cosine. Oh, I said I was just going to use g. So it's 4 minus g. It would be 4 minus that, right? That's big R, that's little r. Because this would be a ring, right? There'd be a ring. Our slice here, I don't want you to forget what you're doing here. There'd be slices here, okay? And the slice would be a ring, all right? So our integral would be pi out in front, big R squared, minus little r squared, and the strips go from 0 to 2. Big R, so you identify that you need vertical strips, you identify that there's empty space. Anytime we're revolving, it's got to be either disc or washer, okay? It's got to be either disc or washer. Matter of fact, that's not a bad thing to throw into our notes back here on this page. These two here are solids of revolution, right? Those two are solids of revolution. So anytime you're talking about revolving a solid, the slices are either going to be solid discs or rings that have empty space. One of those two. The other ones are going to come in when it talks about the base of a solid. Matter of fact, let's just do part C, the other part here, which goes right into that. Okay? Let's talk about part C here. All right, so part C says the region R is the base of a solid. So right there, that clues you in that, okay, this is not one of those revolving ones. This is the base of our solid right here, okay? Let's do that in blue. Here's our base of our solid. Coming up off of the page are going to be some shape. For this solid, each cross-section, meaning slice, perpendicular to the x-axis, what's that mean? Vertical, perpendicular to the x-axis means vertical. Each slice is a square. So that means, let me do that in red. So let's put a strip in here. By the way, let's put a strip right there. Okay? And that is That is what? That strip is what? One side of the square. So coming up off of the page is a square. So it's coming out about here and like this. So here, there, squares. All the way through here, there's squares coming up off of the page. Okay? So what I need is an integral that is the area of the slice times the thickness. Well, I need the area of a square. The area of a square is s squared. One side squared. Well, this strip is one side. So all I have to do, so S equals top minus bottom. So what was the top? G minus F. That's going to be my side, right? That's going to be one side of the square. So my integral will be G minus F quantity squared. It'll be quantity squared, right? Because that's S. That's G minus F. That's one side of the square. And then I need to square that to get the area of the square. And then I would have dx here. And it would go from, again, the strips fill the space, 0 to 2. Right? So, the strip is the key. We understand those are squares coming up off the page. Let's take a look at what they, I guess I didn't check part B. Part B, look what we had. We had 4 minus f of x squared. We had 4 minus g of x quantity squared. We subtracted those, pi out in front. Yep, that's what we had. Look at this one. There's just what we had. G minus f was our s, our side of our square. We square that quantity. We go from 0 to 2. Okay? They would have, I think this would have been acceptable. I don't think you would have had to plug those in. I think they did it. But I don't think you'd have had to. Okay? When it says just write but do not evaluate. All right. And let me show you one more. This is a quick one. You don't have this packet. This is from 2009, but I always thought this was an interesting question. They were really trying to see if people understood what was happening here. Look at part B. Here's your region R. Notice how almost every year there's a problem that's got a region, and you got to do these questions. The region R is the base of a solid. For this solid, at each x, the cross-section perpendicular to the x-axis, again, vertical, has an area of this. Find the volume of the solid. What do you do? He doesn't tell you what shape they are. Is that bad? Why? The only reason we needed to know what shape the slice is so we could find the area. They just gave us the area, right? So what would it be? It'd be the integral of sine pi halves x dx from, I think that's 2. That's it. That is it. Yeah, but I always thought it was a really good question because I'll guarantee you there are people that read that question and said, "Oh my God, I've never seen that before. I don't know what. I have no idea what to do." You know what I mean? But what I like about it is it really gets to the point. Do you understand what it is you're setting up when you set up these integrals? Right? You're setting up area times thickness. If they give you the area, man, they just gave it to you, and that's the only time I've ever seen it. You know, so I don't know. It's been 6 years since they did that, so maybe they're ready to throw one of those on there this year. But I thought that was a pretty interesting one. And then they do another one. They say, okay, here's another solid, the same base. This time they're perpendicular to the y-axis, and they're squares. So that means you'd have horizontal strips, right, perpendicular to the y-axis, and coming up off of there are squares. And so you would have to take those, solve them for x, you know, do a right minus left, and you'd have squares. So you still had to do one like that, but I thought that was interesting. Okay, so here is going to be our homework. Let's do on page 419. This is in that LH packet again. Okay, this is on that LH packet. We're going to do 13 and 15. Now those are a little longer. I think 13 has 4 parts. What they do is they give you a region. So on 13, they give you a region, and then they say, okay, revolve it around this line. Part B, revolve it around this line. Part C, revolve it around this line. Part D, revolve it around this line. So it's the same region, but then you just have to adjust. So some will be discs, some will be washers, that kind of thing. So we'll do 13 and 15. 22 and 25. And then page 4. Now, I'm not going to be here tomorrow, so this is kind of for Monday, too. I mean, you're going to have work time tomorrow. Now, I'm going to have some other things, some other ones of these kind of problems from old packets as part of your assignment, okay? But I haven't figured out exactly which ones those are yet. On page 421, in your, also in your LH packet, let's do 49 A, B, C, and let's do 50 AB. Now again, this is, you should do a lot of this for tomorrow. You will have some time tomorrow during class to do them, but I'm also going to have a few extras too, finishing up some of our old packets to do as well. So there you go. These last two, these are the ones with the like square cross sections and semicircle cross sections. These are all revolving ones. So these are all disc washer up here, okay? And these are all those other types. Okay, go ahead and get to work, and the answer book is right up there on the desk.